Understanding the Zig programming language and its built-in functions can feel like navigating through a labyrinth, but don't worry, I'm here to guide you through each twist and turn. Today, we're diving deep into the core functions that make Zig not only powerful but also a joy to use for systems programming. So far, we covered advanced features of the Zig programming language, focusing on tools that enhance performance like @compile_log for debugging, @compile_error for enforcing conditions, and comptime functions for compile-time evaluations. We also explored generics for reusability and built-in capabilities like @sizeOf, enums, and unions, all improving the quality and performance of our code. Now we will talk about built-in functions specific to memory operations, including the essential @memcp, @memset, and @memove, their uses and why they matter. Now let's see how we can implement the @memcp function to copy memory in Zig. In this code, we declare a source array called sourceData initialized with 5 bytes, 1, 2, 3, 4, and 5. This array serves as the origin for our copying operation. Next, we create an empty destination array named destData, which will hold the copied values. To perform the memory copying, we use the @memcp function passing references to both destData and sourceData. This function is designed to copy bytes efficiently from the source to the destination, ensuring that the destination has enough space to hold the copied data. After the memory operation, we utilize Zig's debugging capabilities to print the contents of destData. The output should reflect the bytes that were copied from sourceData. By employing @memcp, we enhance performance by executing bulk memory operations, which are typically faster than iterating through each element manually. However, it's crucial to ensure that the source and destination arrays do not overlap to avoid undefined behavior, a consideration important in low-level memory management. Now let's see how we can implement the @memset function to zero out the contents of an array. In this example, we begin by declaring an array named data, which is defined but initially contains garbage values. This is where @memset proves to be invaluable. By calling @memset and data 0, we are instructing the program to set every element in the data array to 0. This action is crucial as it effectively initializes the array, preparing it for further use without the worry of residual garbage data causing unexpected behavior. When we run this code, we use std print to display the contents of the data array, which will reveal an array full of zeros, showcasing how @memset can seamlessly reset memory within an array. It's important to understand that while @memset is a powerful tool for initialization, if you're working with sensitive data such as passwords or cryptographic keys, it's advisable to utilize more secure methods like std crypto secure 0 to ensure that the information is securely erased from memory. This highlights the importance of choosing the right function based on the context in which you are operating. Next, we will write the following code to demonstrate the @memove function, which is essential when we need to shift data within overlapping regions of memory safely. In this example, we start by declaring an array called buffer, which contains 10 unsigned 8-bit integers with values from 1 to 10. Now let's see how we can shift the contents of this buffer to the right by 1 position. We achieve this by calling @memove with the destination as the address of the second element of the array, and buffer1 and the source as the address of the first element, and buffer0. This operation carefully handles the overlapping memory regions, ensuring that we do not accidentally overwrite data before it has been copied. After executing this operation, the first element will be lost, while the remaining values will shift to the right, creating a new arrangement in the buffer. Finally, we utilize std print to display the modified contents of the buffer, showcasing how @memove effectively manages memory during this operation, especially in applications like circular buffers where overlapping regions are a common scenario. Now that we've dug into these essential memory functions, let's also touch on some best practices. When working with these functions, always make sure to maintain proper size checks to avoid buffer overruns. It's essential to stay mindful of your memory layout to ensure that the element types between source and destination match up, as failing to do so could result in unpredictable behaviors. Moreover, it's good to remember that Zig is designed for low-level systems programming where you frequently work close to the hardware. This gives you granular control, which is both powerful and, if not careful, dangerous. Memory management and error handling are vital components of programming in Zig, and functions like @memcp, @memset, and @memove are your allies when invoking performance optimizations. Now we've covered the memory copying essentials with Zig, you should feel more empowered to manipulate memory effectively. Remember to incorporate these built-in functions into your projects to leverage performance gains. In conclusion, the Zig programming language provides robust tools with its built-in functions for handling memory, significantly enhancing your coding efficiency. Functions like @memcp, @memset, and @memove empower you to manage memory manipulation safely and effectively while ensuring your program runs efficiently. So far, we have covered the intricacies of the Zig programming language's built-in memory functions. Now you can confidently apply these functions in various scenarios, optimizing your code for greater performance and safety. If you have any questions or need clarification on anything, feel free to ask. Happy coding!